about an invariant that is called birational complexity, which is not in the literature yet, but it will be in a couple of weeks or so. But I will tell you what it is about and what theorems can we get out of this invariant. So first, I will recall the definition of complexity, which is an invariant introduced by Shokuro, but a lot of algebraic geometers have studied it, including Prokhorov, Chelstov, James, McKernan, Brown, Sbaldi, Zhang, and myself. So let X delta be a log pair. The complexity of X delta is, we denoted by C of X delta, is the dimension of X plus the Picard rank of X minus the absolute value of delta. And this absolute value of delta is nothing else than the sum of the coefficients of delta, where this is the sum of the coefficients of delta. Okay, so there are actually a lot of variations of this invariant, but I will go with this, which is the simplest one. So let's see a couple of examples. So for instance, if you take the projective like a P2, so example, and then you put the toric boundary on it. So you put L0 plus L1 plus L2, and compute the complexity of this, you get 0, right? You get 2 plus 1 minus 3. If you take the complexity of P2, let's say with an elliptic curve, then you get actually 2, right? It's 2 plus 1 minus 1. And if you take the complexity of, let's say, the product, the self product of a general elliptic curve, right, you get 5. There is actually no boundary divisor. Right, so notice that I'm mostly looking at Calabi-Yau pairs, because actually this invariant is pretty nice for Calabi-Yau pairs. So there is the following theorem due to McKernan, Brown, McKernan, Sbaldi, and Zhang. So this is a theorem in 2016 that says the following. So I won't write let's say the best form of this theorem, but this is interesting enough. So Brown, McKernan, Sbaldi, and Zhang in 2016, they proved that the following: let X delta be a Calabi-Yau pair, be a log Calabi-Yau pair. So before I keep going, let me just make clear here what do I mean with log Calabi-Yau pair. So X delta is log Calabi-Yau if the two following conditions are satisfied. X delta is log canonical, and Kx plus delta is numerically trivial, but we actually know now by work of Gongyo and Fujino that this equivalent to say that is Q equivalent to 0. Oh, is 0, thanks. Thanks. Okay, so what they say is that if you take a log Calabi-Yau pair, then the complexity is larger or equal than 0, and if the complexity is 0, then X, the round down of delta is toric. So meaning that X is a projective toric variety, and the round down of delta is a torus invariant divisor. So this is a very beautiful theorem. And let me mention that there is some sort of converse, which is quite not obvious, but not hard to prove, that if you take a toric pair with the reduced toric boundary, then the complexity is 0. So this is a characterization of toric varieties within the realm of let's say, birational geometry, because we're imposing some LC conditions, LC singularity conditions. Okay, so what is the birational complexity? Is actually very easy to define. So definition: let X delta be a subpair. So I'm not assuming there is a pair, but it could have negative coefficients, but Kx plus delta is Q Cartier. So the birational complexity that I will denote by Z-vir will be the minimum of all the complexities x prime delta prime, such that x prime delta prime is Crepin equivalent, Crepin birational equivalent to X delta and the coefficients of delta prime are larger or equal than 0, right? So for instance, so Crepin birational equivalent just means that they are birational and there is a common resolution in which the pullback of the log canonical divisors agree, right? So in particular, if this is a Calabi-Yau pair, then I'm essentially minimizing the complexity along all the Calabi-Yau pairs that are Crepin birational to the given one. And then, no, we're not assuming Q factoriality in this term. Yes, but this should still be fine. Yeah. Okay. So we need to. Okay. So let me write Q factorial here. Okay, but let's we can discuss that later. Actually, from what I will say next, we can always assume that these varieties are Q factorial. So and then we will define the alteration complexity that I will call C alt x delta, which is the minimum of the birational complexity of x of y delta y, such that y delta y to x delta is finite Galois crepant. So what this means is a finite Galois morphism, and the pullback of kx plus delta is ky plus delta y. Okay, so this is the definition of birational complexity, and the second one is what we will call alteration complexity. So let's see some examples now of this invariant. So let's write the following. So examples. So I will write xn, bn to be p1 to the nth power, and here I will just write bn to be the torus invariant divisor, reduced torus invariant divisor. And now I will consider the involution that acts as follows. So you have x1 y1 to xn yn, and this will go to y1 x1 all the way to yn xn. Okay, so now I will quotient, and I will obtain a new pair that I will call yn delta n. So observe that the involution preserves bn, so you can actually get a local Calabi-Yau pair which is the quotient of these. So this will be xn bn, quotient by this involution. I should index it by n as well. So n here is larger or equal than 2. To get something interesting. Okay, so let's write a table with the complexities of these objects, the birational complexities and alteration complexities. So let's look at xn bn first. So this is a toric pair, right? So it has exactly 2n components. This guy has exactly 2n components. The Picard rank is n and the dimension is n. So the complexity of xn bn is 0. So let's write here xn bn. Here I will write yn delta n, and here I will write complexity, then the birational complexity, and the alteration complexity. So let's see what can we say. So xn bn is toric, right? So the complexity is 0, and then of course the birational complexity and the alteration complexity are 0 because these are minimums among finite covers or birational transformations of the pair. So let's see what we can say for yn delta n. So if we compute the complexity, so let's think about how this acts on the Picard rank, on the Picard group, right? So you see that it will map each toric divisor to the only other prime toric divisor which has the same class in the Picard, right? So actually this action acts as the identity on the Picard. So the Picard of the quotient is actually n, and you have 2n components, but in identifies them 2 by 2, right? So when you quotient, you get exactly n components. So it's easy to check that the complexity of this guy is n, The alteration complexity is 0 because it's actually the quotient of something toric by definition. And then the question is, what is the variational complexity? Well, we can say it's at most n, right? But it's actually super hard to compute this, even in this example, because you see you have to go to all the possible Crepin variational models. And that's like some sort of non-finite type game, right? So actually, I don't know how to compute this without one of the theorems I will introduce next. Okay, so let's go to the theorems. So you may need to, no, not always. You may need to actually go to some other model, contract divisors first, and then take a DLT blow-up of some other variational model. So it's not true that the one that computes the variational complexity will dominate the starting one. For instance, for a simple exercise, you can take P2 with the lines and start blowing up points that are not zero strata here, and then contract L0, L2, and L0, L1, and L2. So you get no boundary divisor. You need to go back to P2 to compute the variational complexity. So now I will write one more definition, and we start with the theorems. So let me keep the table there because it will be useful for what I will say next. So the last definition for now is the following. So let X delta be a local Abelian pair. The co-regularity of X delta, the co-regularity of X delta is the following quantity. The co-regularity of X delta is equal to the dimension of X minus the dimension of the dual complex of X delta, which is a combinatorial, is a CW complex that tells you how the DLT centers of a DLT centers of a DLT modifications of this object intersect minus 1. So the co-regularity is an invariant that essentially measures the singularities of the pairs, and the co-regularity belongs to 0 and it's actually equal, the co-regularity of X delta equals the dimension of a minimal log canonical center in some DLT modification, and here you can replace some by any DLT modification. So now I will state the first two theorems of this talk. So the first theorem is work in progress with Mirko Mauri. Actually, the first two theorems are work in progress with Mirko Mauri. So theorem 1 and theorem 2. Are there any questions so far? Okay, so theorem 1. And just as a comment, right? So these two pairs have co-regularity 0 because they have this 0-dimensional strata in which all these toric divisors intersect. The 0-dimensional strata here descends to a 0-dimensional strata here. So the co-regularity of these two pairs is 0, or these infinitely many pairs if you vary n. So first theorem is work with Mirko Mauri, hopefully on archive in a few weeks. So let X delta be a local Abelian pair. Then the variational complexity of X delta is bounded above by the dimension of X plus the co-regularity of X delta. So in particular, if we apply this theorem to this setting, we obtain that the variational complexity of this one is at most n. So it's not very useful so far, right? So let me just say in words what is the proof of this theorem. It's actually not so complicated. It's essentially mostly motivated by the work of Cochet on towers of Mori-Fiver spaces. So it's essentially taking some DLT modification and study the possible towers of Mori-Fiver spaces and then counting devices with coefficient 1. So let me say that it's not so complicated. So the second theorem is more enlightening and more useful. So theorem 2, again by Mirko Mauri and myself. So let X delta be a local Abelian pair of dimension n. So first, so if the birational complexity is less than the dimension. So if you're in Cor-regularity 0, this is the maximal possible variational complexity is the dimension in Cor-regularity 0, right? So this will be like almost all cases in some sense, okay, that we will explain later. So if the variational complexity is non-maximal, then the dual complex of X delta is union of two collapsible subcomplexes. And further, if further, so assuming, keeping this condition, and if further the dual complex is smooth, then the dual complex is either PL isomorphic to a sphere, or the dual complex is PL isomorphic to a disk with K less than or equal than n minus 1. Okay, so there are essentially three components of the proof of this theorem that I will proceed to explain. So we use some tools from birational geometry, some tools from CW complexes, and some tools from topology. Yes, so these dual complexes are almost always connected. I mean, they're always connected unless there are just 2 points. And the 2 points case is S0. Yes, so yes, indeed. But I mean, it is related, but we actually, I mean, it's actually non-trivial from the literature. I mean, so far what we know about this object is that it's a pseudo manifold of dimension at most n minus 1, and if it is disconnected, it's just 2 points. So this is what we know. And now essentially what we're trying to say is that quotes almost always is a sphere or a disk. But now we can give an answer to the variational complexity of this object, right? Because here the dual complex of yn, oh, I think sorry, I missed one condition here. If further this is smooth and the dimension of dx delta is different than 4. Okay, so for the people that know topology, this is related to the Poincaré conjecture. So we need to use the PL version of the Poincaré conjecture to prove the last step. So I think we have to ask other people about that case. Okay, so then we can go back to this. So what is the action of In in the dual complex? The dual complex is a cube here, right? And the action is just the antipodal action. So the quotient, the dual complex of this is just P n minus 1 R, right? But this guy is not a disk, it's smooth, it's PL smooth, but it's not a disk or a sphere. So what we conclude this is equal to n whenever n is different than 4. For n equals 4, I don't know how to compute this, and it's very sad. Okay, yeah, this looks, sorry, n should be different than 5, because I want the dual complex to not have 4 dimensions. Okay, so let me go to the, yes, yeah. So for this case, yeah, for the RP2 case, you're actually right. So the first part suffices. Yeah, thanks. But still, what I want to say is that I don't know how to compute this without using the theorem. So let me tell you about the proof of the theorem. So here, as I said before, we use tools from 3 different sources. So the first source is birational geometry. The second source is some connections between CW complexes and MMP, and the third source is topology. So we use some very basic topology, or let me say it in different words, we use very advanced topology in a very basic way. So let me tell you the sketch of the proof. So a sketch. So there is a lot of work by Kolar and Chengyang and by Sbaldi and Filippazzi that if you have a Calabi-Yau pair, okay, so if X delta is a Calabi-Yau pair, you can find these models that I like to call Collar shoe models, which is a variational, Crepin variational transformation that transform it into X prime delta prime that has a vibration onto Z that satisfies the following conditions. So this can be chosen to be Q factorial and ample, sorry, Q factorial and DLT. And then the condition is that all LC centers of X prime delta prime are horizontals over Z. And the round down of delta prime supports an ample divisor over Z. Okay, so one can construct models like this. So let me just tell you what the punchline is with this variational complexity, is that if we assume that the variational complexity is not maximal, so if the variational complexity is less than the dimension, then this implies that we can choose this birational model such that the round down of delta prime properly supports an ample divisor. And then what we do is that, so let's call it ample over Z. So this is horizontal, so it won't. Properly is that you can throw away one component, and then the rest of the components support an ample. So precisely this means, right, that there is a component E here, such that the round down of delta prime minus E supports an ample over Z. And then, okay, so then the idea is to, so let's call this ample over Z A. So then what we do is that we run a Kx plus Kx prime plus delta prime minus E MMP over Z with the scaling of A. Okay, so by the work of the Fernet, Collar, and Xu, what we can say is that this MMP, so let me call the steps X, X1, X2, and so on. So observe that this is not pseudo-effective over the base. So it must terminate with a modifier space over Z. So let's call it xk over W. So this is a modifier space over Z. And this whole MMP is over Z, right? But the point is that since we're running a scaling of A, and A is contained here, what we can argue using the work of the Fernet, Collar, and Xu is that the dual complex of xk round down of delta prime k minus ek, so these two guys are just the push forward of these two in the corresponding model. So for each step, this is a collapse. It's a simple collapse. So now we just need to study this dual complex on K. Oh, I'm using K for two different things. Sorry. This should be I. Okay. So this is a simple collapse for every I, starting from this that we can say that is X0. Okay, but then what happens in the last model? In the last model, you have the dual complex of xk, the round down of delta prime k minus ek, and this is, so this pair inside, not the dual complex, but the pair inside is DLT Fano over W. Okay, so what is the, so then what you do is compute the dual complex of this, which will be isomorphic. So PL, or actually isomorphic as CW complexes. So the dual complex of a DLT Fano pair is just a simplex. So here you will have some simplex. Let me call it omega L. And then you have to intersect also to understand this dual complex, you have to intersect with the vertical strata. But you can prove that actually this is just doing joint with a dual complex on the base. So for some divisor VW. But then you're doing joint of a simplex with something, so it's collapsible, regardless of what this something is. So this is collapsible. So what we conclude is that if we throw away E, so essentially if we throw away a point and the whole link of that point in my dual complex, then I get something collapsible. And of course, the link of the point is collapsible. So we prove that it's a union of two collapsible subcomplexes. So this finishes the first part of the proof. So we just proved this. Okay, so now the topological part of the proof. BW is just some. This is just some boundary obtained by the canonical bundle formula from the pair here. So yeah, but it doesn't matter what it is, right? We are doing joint with a simplex, so it's collapsible anyways. So what is the topological part? So how we conclude the last part? So here actually we have to use the Poincaré conjecture in the PL category. So what we know, so now we are assuming that the dual complex is smooth, and this is vital for the proof, because I mean, if you have a teardrop, right? Just think about a teardrop. The teardrop is a pseudo. You can think about it as a pseudo manifold that is union of two collapsible subcomplexes, but it's not a sphere or a disk. So we really need a smoothness in this part of the proof. So what is known and is classic, right? This is the statement that you find in any topology book, is that a collapsible manifold is a disk. It's a PL disk. One can write PL here, right? So what we have concluded so far is that now we're assuming that it is smooth and it's a union of two collapsible subcomplexes. So it's a union of two disks, right? But so if you have studied a bit of topology, you know that this is a bit. You have to be a bit careful, right? There are topological objects that are union of two spheres, of two disks that are not diffeomorphic to spheres. It really depends on which category you're working. If you're working up to homeo, PL, or diffeomorphism, right? So one has to be careful. So if you just taking some thickening of these disks, I can assume that the disks look like this. So the first disk, let's say, is D1, is this, D1, and then the other disk here is D2. So by taking the thickening, I can assume that the intersection is actually, again, a smooth PL manifold, a PL manifold. So we can assume by thickening, assume D1 into D2 is a PL manifold. Okay. If there is no boundary, we know that it's collapsible, period, right? So it's a disk immediately.
Yeah, but sorry, when you say collapsible manifold, you mean like
with no boundary, yeah, with no boundary, right? Because if there is boundary, we already know that it's collapsible, right? This is in your paper with right. So from now, yeah, we can. Sorry, I forgot to say that, but from now on, we can assume there is an open manifold, because in the case that the dual complex has boundary, we can prove directly that it's collapsible. So if we assume that it's further smooth, then it's a disk. Sorry, I forgot to say those words. Okay, but the Peel-Schoenflies conjecture tell us that D1 inter D2 is a PL annulus. So what is the Peel-Schoenflies conjecture, which is known in the PL category in dimension n different than 4, right? So this says that, I mean, it's a generalization of the annulus theorem that says that if you have some manifold whose boundary is union of two spheres, then it must be an annulus. Okay, again, this is true in the continuous category, it's true in the PL category, but for in the up to diffeomorphism, this is not true. Okay, so we can replace D1 with D1 minus D2 and D2 with D2. No, I don't need to replace D2. Sorry. I just replace, I do this replacement, and now by this, I know that this is still a disk. So, and dimensional PL disk. But now, since I have that these are two PL disks that intersect as at a sphere of dimension n-1, right, I conclude that this dx delta is PL homotopic to a sphere of dimension n. And then Smale tells us that this is a PL isomorphic to a sphere as long as n is different than 4. So that's how the proof goes. So then dx delta is PL k n-1 when n is different than 4 by Smale's proof of PL point correct conjecture. Okay. So, and okay, here I say the open of dimension n, but you see I didn't use n in the whole proof. I mean, you just replace by k for the other cases. And if it has boundary, we know directly that it must be a disk. Okay. So that's the first, or that's the second theorem. And now let's jump to the third theorem of the talk, which is probably the last that I will be able to explain details of. So far we can say that if you have a local Abelian pair of Cor-regularity 0, right, the birational complexity moves between 0 and n. And if it is not n, you conclude something nice about the dual complex. So in other words, if you have any interesting dual complex, it must have maximal birational complexity. So this is the direction that I like to think about this invariant. So now I will prove a theorem that actually says much more than the previous one. So it actually tells you something about the geometry of the pair rather than just the topology of the dual complex. So the third theorem is work in progress by myself. So theorem M23. So now actually I need to impose an extra condition, and I hope to take it out in the future, but so far I don't know how. So let x delta be a n-dimensional local Abelian pair with kx plus delta is 0, linearly equivalent to 0, right? So now we are in the case of index 1 Abelians. Okay. So if Z is the birational complexity, then X has a birational model that admits a tower of Mori fiber spaces of which at least n minus c are conic bundles. So essentially, what I want to say here is that if your local Abelian pair doesn't have maximal birational complexity, then you find some interesting conic bundles structures. So for instance, X cannot be birationally rigid if you do not have maximal birational complexity. So essentially, if you put these two theorems together, you get some interesting implications. So if you have any interesting dual complex, then you must have maximal birational complexity. And if X is birational super rigid, then it must have maximal birational complexity. Okay, so let's do a sanity check here. So if the birational complexity is 0, then this means that X delta is Crepin equivalent, Crepin birational equivalent to a toric pair. But every toric pair is Crepin birational equivalent to Pn and the hyperplane coordinates, right? If we are under the assumption that kx plus delta is 0. But then you can make this birationally Crepin equivalent to P1 to the n, and then whatever toric boundary we called before Bn, and this one has n conic bundles, right? So they're actually toric conic bundles, and I can write more details of the theorem, but let's keep it like this for now. But these toric bundles that I cook up are actually toric in the sense that there are predictivizations of some line bundles on the base. So So let me tell you what are the main ideas. So again, I will do a sketch of the proof of theorem 3. So the main ideas comes from 3 different, let's say, from 3 different places again. So the first one is equivariant birational geometry. The second one is automorphisms of Calabi-Yau pairs. And the last one is historic geometry. So let me sketch the proof for you. So actually, I will sketch the proof in the easy case because the whole proof is much more intricate than the first one. So I will just try to write the sketch in the easy case. So sketch. So what it means to have non-maximal birational complexity. So the idea is that if you have some interesting birational complexity, you can cook up a new model, x prime delta prime, such that, so here delta prime is reduced, right, by the conditions of the theorem, and delta prime has let me think for a second, has more components than rho of x prime, right? So essentially, this is what it means, that so if you have birational complexity n-1, it means that you can find a model where this guy has 1 more component than the Picard rank, and if you decrease the birational complexity, it means that you have more components, right? So we can find d1 through dn-1 Weyl divisors supported on the round-down of delta prime, all of them linearly equivalent to 0. Linearly equivalent to 0, and each dj has a component not contained in the other's di's. Okay? So then what we do is that we will take xp to be a spectrum, the relative spectrum over x prime of the following algebra. I will take alpha in zp to the n-c. Here, p is a large prime number, and here I will write alpha 1 d1 all the way to alpha n-c dn-c. Okay, so if I take this relative spectrum, essentially what I'm constructing is a cover such that here I have a zp to the n-c action, and if I quotient by this group, I will go back to x prime delta prime. Okay, so now the idea is to run a zp to the n-c equivariant kx pmmp. So, and now I will cheat, and I will say that it terminates with a modifier space to a point, okay? Because this is the easy case. The other case is much more intricate. So assume it terminates. Sorry, I forgot one detail. So I may assume that this guy is DLT. I may assume that this guy is DLT. So XP is canonical, right? Because what I want to use is BAV in the outcome of the MMP. So if I don't take a DLT modification that I can do equivalently, I mean, I cannot say anything about the model that it terminates. So assume it terminates with a modifier space to a point. No, it's a finite bundle. It's like there's a G torsor. It's a set P n-c torsor. Right, because these guys are torsion, right? So, yeah. So then what you get is that you get xp, and then you run this equivariant MMP, and it terminates in x prime p, where this is canonical bounded, or canonical Fano, right? So in particular, these guys are bounded. So if I push forward my boundary, and I know that some of you cannot see this, so So if I push forward my boundary, I get that this guy is Calabi-Yau and bounded as well in terms of the dimension. So, okay. So I will leave that one there, and I will continue with the proof here. So what is the point is that now, since we run an equivariant MMP, oh yeah, because it's integral. So every other model is integral. Delta is integral, right? So this is an integer. Yeah, I'm assuming it's kx plus delta is linear equivalent to 0. It's not q equivalent. So that was the condition that I say that I would like to take out. Yeah, no, don't worry, don't worry. Yeah, so this is a condition that I'm pretty sure one can take out, but at least my proof doesn't show how. So then we have set p to the n minus c inside out of yp, sorry, xp prime, delta p prime. But this is bounded in the sense that we know that the automorphism group of a Calabi-Yau pair, where when xp prime is of Fano type, this guy must be a finite extension of gmk for some k. Or did I use k? No. So we know that this is a finite extension of gmk, and since these log pairs are bounded, I can bound the size of the finite extension, right? Since I pick p to be a large prime number, I can assume after running the proof again and replacing p with a larger prime, I can assume that this will factor through an n minus c dimensional tori action. And then the rest is toric geometry. So using toric geometry, you start finding birational models in which you can take quotient by gm one at a time. And right, but this is happening on some equivariant model. So then the punchline is that you have x prime here, delta prime. If you quotient by z n minus cp, you get to a different model, right? So we run an MMP. So we don't go back to x prime delta prime, but we will go back to something x prime prime delta prime prime that is birational equivalent to x prime delta prime. And then you find a birational model here that has a lot of conic bundles because we have this torus action. So we can, in some birational model, we can start quotienting by one by gm, producing toric conic bundles. So then you do the same here. So, okay, I don't want to introduce more notation. So I think at this point, the proof may be a bit clearer. So quotient by gm and so on. And then you quotient, and since this group, zp to the n minus c is inside gm, when you quotient, the quotient is also a toric conic bundle. Quotient by cp minus c, and then you produce a new model here. Okay, I'm running out of letters. I don't use many letters so and this is the end of the proof. So yeah, sorry, that last part was a little bit rushy, but that's exactly because of this condition that each dj has a component. Mm-hmm. Oh, sorry. Yeah. I divide by p. So you really need to go to the p. Sorry about this, right? So you really need to go to the p power to get something torsion. By this condition here, this divisor is torsion if and only if p alpha is 0 here. So this tells you it's connected. Yeah, but that doesn't matter. I mean, you're just taking taking like a subspace of the Cox ring. Uh-huh. Right. No, but you divide by p here, right? So now this is a Weil divisor that is torsion. But when you take the index 1 cover, you will ramify it along the divisor. So is this in the case of Pn, this is a Harshon covering trick, right? You will get a weighted projective in the cover. Yeah, we can discuss it, the details later. So now in the last minute, let me. So I mean, so some other way to see it is that each of these guys are, so each di is diff of a rational function, and then I'm taking the p square root of f, and then I'm taking the closure of x in this larger field. So and that's for sure connected. So I mean that's another way to see it. Okay, so let me finish the talk by discussing about Fano varieties, right? Because so far we were talking about Calabi-Yau pairs. So now let's talk about Fano varieties, and I will finish with a question that is the embarrassing question of this talk. And many of the things that I mentioned are about the birational complexity, but let me just say in words that similar theorems holds if you work with the alteration complexity, but then you need to take finite covers in the proofs. I mean, you need to take finite covers in the statements. So Fano varieties. So if you have, so this was the last section, I think. Fano varieties. So if you take X, an n-dimensional Kelty-Fano, you can define its Cor-regularity to be the minimum of all the Cor-regularities of log Calabi-Yau structures on X. So X delta is Calabi-Yau. Right, so essentially this means that X is exceptional if and only if the Cor-regularity is equal to the dimension, right? And we know that those are bounded. So philosophically, most Fanos should have Cor-regularity 0. So the Cor-regularity belongs to 0 up to n. And we prove the following theorem with Figueroa, Filipazzi, myself, and Junjiao Peng in 22, that if X admits if X has Cor-regularity 0, then it admits a 2 complement. Right, so you can take this 2 complement, let's call it gamma, and then you can take the index 1 cover of kx plus gamma, right? So you have 2 kx plus gamma is linear equivalent to 0, and then you can take the index 1 cover y gamma y. And now this satisfies the conditions of the previous theorem. But first, let me recall that by theorem 1, the birational complexity of gamma of y comma gamma y is integral and belongs to 0 up to n. So theorem, let me just recall theorem 1. So I have until 35, right? Is that fine? Okay. So let me not write all the hypotheses, but under the hypothesis above, the birational complexity of this guy belongs to 0 n. And by the last theorem, right, we get that, and if the birational complexity is less than n, y has birational conic boundaries. Okay, so this is just an application to Fano varieties, but it's a straight application, right? I mean, I didn't prove anything. I just wrote the theorems in a different, I just applied the theorem in the straight way. But let me just make a comparison with the smooth hypersurfaces. So let's see what happens for the smooth hypersurfaces. So a smooth Fano hypersurface. So if you take xd inside Pn, a smooth Fano hypersurface, and d is less than or equal than n, then well, d must be less than or equal than n if you want it to be Fano, right? So then what you can do here is that you can project out of d points, and then you get a map, a rational map to Pn minus d, where the general fiber is an index 1 Fano, a smooth Fano variety. And then you can recompactify ransom MMP. And you can do the following. You can find a virational transformation to X prime D that has a Mori fiber space to P1 to the n minus D, right? Hopefully my indexes are correct, yeah? So essentially what I want to say is that for Fano varieties of co-regularity 0, we have this birational, so this is sort of canonically defined birational complexity that comes from the index 1 cover of these two complement. And then, so the philosophy here is that you can think about the birational complexity of a Fano as being the degree of the hypersurfaces minus 1, right? So Fanos of birational complexity 0 behaves pretty similar as a smooth Fano hypersurface of degree 1 and so on. And one can prove actually a lot of comparison theorems. So what is the embarrassing question now? So we have seen that there are examples of Calabi-Yau pairs that have Calabi-Yau pairs that have maximal birational complexity. But we started with these two examples, and both of them had alteration complexity 0. So the embarrassing question is that I do not know how to construct Fano varieties or Calabi-Yau pairs with maximal alteration complexity in each dimension. So they probably exist, but I just don't know. So Anne-Sophie Kalogiros have these examples of Calabi-Yau trifles that have co-regularity 0 and no toric model. So those must have maximal birational complexity, but we do not know if there is some cover of them that will have non-maximal birational complexity. So this maybe this is a question. So let me pose the following conjecture, or yeah, let me write it as a conjecture, and then I will write this conjecture. And since I have a few minutes, I will write a last theorem, but I won't be able to explain the details. So conjecture: every in any dimension n larger or equal than 4, there is a terminal Fano hypersurface of degree n in Pn with alteration complexity, which is just the alteration complexity of X is the minimum of all the alteration complexity of Calabi-Yau pairs equal to. Okay, so and let me tell you why I propose this conjecture. So the conjecture is motivated by the last theorem. So for the last theorem, I won't be able to give the sketch of the proof, but it's sort of let's say it's a bit clearer from the previous ones. So let's go with this is theorem 4 now. Yeah, terminal singularities. Because if we say smooth, yeah, actually, maybe one can say smooth, but if we say smooth, we don't even know how to construct a sample with birational complexity n. Right? The examples that we have of birational complexity n, they tend to be terminal Fano hypersurface of degree n. So my hope is that we can construct examples of maximal alteration complexity in this setting as well. Okay, so the last theorem, theorem 4, is the following, which essentially is some sort of birational decomposition theorem for Fano varieties of co-regularity 0. So theorem 4, again, this work in progress. So let X be a Fano variety of co-regularity equal to 0. There exists a KLT projective variety X prime KLT projective variety X prime obtained from X by a finite Galois covers and birational transformations satisfying the following. One, there is a tower of modifier spaces. There exists a tower of, let me just write, of modifier spaces, x prime, x1, let's say all the way to xr. And two, the general fiber of each x, this is x0, okay, xi to x plus 1 is either a, okay, actually a is contained in b, but it's good to separate it, a rational curve, or a terminal Fano of Cor-regularity 0 and maximal alteration complexity. So equal to the dimension. So in other words, what I want to say with this term is that if you are interested on Fano varieties of Cor-regularity 0, that are most, like quotes, should be most of the Fano varieties, up to variational transformations, you can decompose it in rational curves and terminal Fano varieties of Cor-regularity 0 and maximal alteration complexity. So these two varieties should be the building blocks of Fano varieties of Cor-regularity 0 in general. So it, so essentially theorem 4 tells you that there is these two building blocks, but yet we don't know if the second building block is empty or not. So it's a little bit of an embarrassing situation, but I'm pretty sure that people will come out with examples of this soon. Okay, I think I will finish here.